So here, during the start of the recording, it removes few of the people, students. So please ask those students who removed. I have given message on the group also, but still ask to rejoin the people so that they can attend the lecture. So here we were talking about the procedure for computing the F closure. So we are applying three rules, that is reflexivity, augmentation, and transitivity. So these rules we have to repeat unless and until the F plus doesn't get changed. So F plus closure of a functional dependencies is a set of functional dependency which are logically implied by the given set. So whenever any set is given, so that set can logically imply many functional dependencies. So in order to calculate this, we are applying this uh, Armstrong axioms, and there are many other rules also. That is additional rules, union, decomposition, and pseudo transitivity. Union, it means that we can go for union on the right hand side. I will wait for 5 minutes. Still people are joining and I need to shift within the windows. So I will wait for 5 minutes more. We will start now. So here there are again additional rules are there to perform a calculation of closure of functional dependencies. So alpha gives beta if this functionality holds, then and also alpha gives gamma. This functional dependency also holds. Then we can combine the right hand side as we are having the left hand side same as for the both functional dependencies. Then we can combine or perform the union that alpha gives beta gamma or alpha holds on beta gamma. So this is the union rule. Next is the decomposition rule. So if we are having the dependency alpha gives beta gamma, then we can distribute this alpha gives beta and alpha gives gamma. So this decomposition union is made in order to have any other functionality dependency existing for this, then we will perform the union. And if any other functional dependency holds on beta or gamma, then we can apply the transitivity rule, and that's why these functional dependencies either perform union or either perform decomposition. And also there is one more rule is there, pseudo transitivity. Pseudo transitivity, it means that we let it feel that we are performing the transitivity. So here we are having the alpha and we are having alpha holds on beta. If this functional dependency holds, and there is also functional dependency gamma beta holds on delta, then in order to match this right hand side with this left hand side, and in order to add one more transitivity rule, we add gamma on the both sides of this functional dependency. So adding this gamma on the both side,
Ma'am, sorry for interruption, but your screen is not visible.
is it
Means the procedure for computing F plus, that slide only visible to us.
closure of functional dependencies?
No, ma'am, no.
Okay, let me present it twice. Previously also same slide was visible.
Yeah, ma'am, previously also.
Now which slide is visible to you?
Uh, Up till now, there is a no slide visible to us. Just wait for a while, ma'am, because it's take time to visible to us, visible on our side.
Okay. Thing is that when I jump to the presentation, I don't see your chats, etc. That's why I haven't seen. Now is it visible?
No, ma'am. Means it takes few minutes or 2 or 3 minutes more on our
Okay.
side.
Okay. Now is it visible?
Yeah, ma'am, it's visible now.
Closure of functional dependencies,
Yeah, this slide is
additional
visible.
rules.
Yeah. Ma'am,
Okay.
why you are not opening in the presentation mode?
Actually, presentation mode, I cannot perform the changes in the presentation mode. Okay.
Okay.
During the explanation, etc., I used to take an example. I need to write something. That's why if I shift to the presentation mode, I cannot write. Again, I need to press escape and come to that window. That's why I don't use the presentation mode. Okay,
Okay.
let us use the presentation mode, and whenever it needed for the writing, we will jump to the uh, previous screen. Okay. Now whether presentation is visible to you?
Yeah, ma'am, it's visible.
Okay. So shall I repeat the additional rules?
Yeah, ma'am.
Okay. So, for calculating the closure of functional dependencies, we are using the three rules, that is reflexivity, augmentation, and transitivity. Even though these rules are sufficient to calculate the F closure, there are also additional rules are there. It means equivalent rules are there. So these equivalent rules are called as the additional rules, and there are three rules: union, decomposition, and pseudo transitivity. So union, it means that whenever I'm having any functional dependency, alpha gives beta and alpha gives gamma, then we can go for combining the right hand side, that is beta and gamma. We will perform the union because left hand side alpha and alpha, this is matching. So in order to combine these two, we can perform the union. It means alpha gives beta gamma. Here, union on the right hand side is done. So union of alpha and alpha gives alpha, the only single variable it gives. Next, decomposition rule, it means that whenever we are having the new functional dependency, alpha holds on beta gamma or alpha gives beta gamma, then we can distribute these two variables or these two attributes. Alpha gives beta and alpha gives gamma. So here decomposition, union, these rules are applied in order to have more combinations and whether any other functionality dependency existing for this left hand side or this this right hand side or this right hand side, so that we can go for applying much more rules. So it means here if any other functional dependency holds that beta gives gamma, beta gives delta. In this case, we cannot apply this functional dependency directly on this variable. So for this purpose, we need to distribute or decompose this. Then alpha gives beta and beta gives gamma. Beta gives delta. That we can write. And here this is a decomposition rule, and pseudo transitivity rule. It means that if we are having alpha holds on beta and there is a rule gamma beta holds on delta, then we can add gamma variable on both sides of this functional dependency, alpha and beta, and then we can say that as right hand side is matching, then we can write that alpha gamma gives delta. So this pseudo transitivity rule is applied. So clear with these rules?
Ma'am,
So let us start with the next point.
ma'am,
Yes.
can
Yes,
you
am I audible?
give, yeah, you're audible. Can you give the example of pseudo transitivity?
Yes, I can. Let us go for the example. Here, right now, here we are having A gives B and we are having A gives C. These two rules are there, and
Ma'am.
CG gives H. Okay. So now
Ma'am,
here, yes,
ma'am, only that closure of function dependency side is visible to us.
why it is not visible to you? Whenever I'm pinning my presentation to the chat window, it completely shows me the slide. Okay, now whether example slide is visible to you. Wait a.
Ha, ma'am, now it is visible.
Okay. So this is a set of functional dependencies, and right now I'm having the functional dependency is A gives C and CG gives H. Now there, whatever this left hand side is there, this is not equivalent to this left hand side C. C and CG. There are two variations are there. So in order to make the pseudo transitivity, what we will do, we will add G on the both sides, okay, and then write CG, okay. C attribute is added on the both side. Then I'm having right now this right hand side matching with the left hand side. Then I can say that for this we are having the dependency on the H attribute, and then I can say that AG gives me H. Okay. So pseudo transitivity, AG gives CG and CG CG gives us H. So this functional dependency is called as a pseudo transitivity. Usually transitivity it means that A gives B and B gives any other variable H. Then we can say that A gives us H. But here,
Ma'am,
whatever, yes,
sorry for interruption again, but you are typing now.
yes.
But what you made the changes in that slide means you are typing that changes are not visible to us. Means due to noise, I able to understand means you are typing, but that changes is not visible to us.
What is happening actually?
Ma'am, you ask means it's happened with me. It is not clearly understand to me. You can ask anybody. Means
Screen is not visible. Okay, whether can you see AG gives CG whatever changes I have done? Remaining students, it is not, it has visible very light. Okay. Any other opinion?
ma'am, it takes time to means visible on our side.
Okay, let me share the entire screen. So now let me check whether whatever I am typing, is this visible to you? Is this visible? A, B, C, D typing?
Yes, ma'am. Yes, it's visible now.
Okay. Today we are getting too much disturbance in the lecture. Outside also some work is going on. Okay. I was about to giving the example for the pseudo transitivity. So usually transitivity it means that if we are having A gives B and again we are having B gives H, okay. So here whatever existing example is there, within that whatever the right hand side is there, this is equivalent to the left hand side of this, and here we need not to go for any other addition of any attribute. Directly we can say that A gives H because here we applied the transitivity, okay. But whenever there is no matching AC and CG, here there is no matching for the right hand side and this left hand side. So for this purpose, to match this left hand side and this right hand side, we go for adding the G attribute on the both sides. Okay, G attribute will be added on the both sides, and hence AG gives CG. This will be given to this functional dependency we can uh, imply, and then CG gives H, and then we can say that AG gives H. So this is a pseudo transitivity. Now understood? Whether changes are visible? Whether changes are visible? Okay, yes. So right now entire screen is shared. That's why whenever I go to the chat for looking for the chat, it shows the nested loop of the same window. So this is a pseudo transitivity. Union, it means that right now we are having A gives B and A gives C. So here we can say that A gives BC. So this is a union. Okay, this is a union, and here right now we cannot go for having decomposition. Decomposition, it means that whatever this rule is there, we can go for saying AG gives C and AG gives G, but there is no point in this. So AG gives A gives BC. This here we applied the union rule, and again CG gives HI. This also rule we can imply from this. Clear with these rules? May I move to the next point now? So okay, let us move to the next point now. So we have also started the exam explanation on the closure of attribute sets. So closure of attribute sets, uh, it means whatever this every attribute set is there. For this purpose also we can calculate the closure. That is, right now we are having the functional dependency A gives B, A gives C, CG gives H, CG gives I, and B gives H. For every left hand side, if we calculate the closure, that is which other functionalities are implied, then we say that that is a closure of that element. So here, just like we perform the union, now here we make the conclusion that as B gives H, I can add the attribute H also. As A is itself, we can add the A also. Again, it means this much possibilities are available. So this complete implied possibilities and union, this will be given by the A closure. A closure, it means that this is a attribute closure. Whatever the left hand side attributes are there, which are possible functional dependencies or attributes are there, that we are combining together. So this is a closure of A. Now, if we take a CG, we can take CG, HI, etc. Then we can say that this is a closure of CG. So let us see the definition of this. Given a set of attributes A, define the closure of A under F. So this is a set of functional dependency denoted by A plus as a set of attributes that are functionally determined by under A under F. So for A, those which are attributes dependent on that, those all we perform together. So here, this is our algorithm that B gives gamma, we can add. If B is available in any of the functional dependency, then we can add B to the beta to the result. So for this also, we are going to see, we have seen this example yesterday actually on the Thursday, that here we calculate the closure of AG. So AG gives us the complete set R, and that's why this is a super key, that on the super key we are having this dependent. So anybody want me to repeat this? Students are still joining. Anybody want me to repeat attribute closure?
Yeah, ma'am, repeat it.
So here, in this example, previously we calculated the closure for AG plus. Now let us calculate the closure for, uh, let us take A. Okay. So this example right now gives us the A. So here we are looking, we will follow this algorithm. So result equal to A. It means right now current functionality is there. That also we will apply. So initially, whenever we are moving towards this example, so initially result, this is the left hand side. Okay, left hand side, it means this is a beta. Right now in the result, whatever attribute is there, that will be added to the existing result. Now in the functional dependency set, F is a set of my functional dependencies. So within that, I will check whether any functional dependency is available where this is available on the left hand side. Okay, whether a attribute is available on any of the left hand side. If available, whatever this beta variable is there, that also we will add to the explanation. So here closure, this says that changes to the residue for each beta gamma in F if B is a subset of result. Okay, in the result right now I'm having A available because I wanted to calculate the A closure. Okay, A closure, initially whatever A is there, that will be added to the result, and hence I have added the A. If there is a functional dependency beta gamma existing and beta is a subset of result, right now here attribute A is a subset of result because in the result we are having A available. So what it says, then result should be equal to result union gamma. Okay, so it means whatever the functional dependency starting from A is there, those all functional dependencies we need to add to the result. So let us apply this rule. So here A, from A we are having B, so we will add B to the result. In this, again, any other functionality is not implied here because here A only single is there. This also, see, AJ is there, so which is not equal to the A. CG not equal, CG not equal, B is available. Now, this beta gamma, beta is a subset of result. Okay, so B is a subset of AB. So whatever H is there, that we will add to this H. Done. So here we added the H to the result. Now here we are having AG gives CG. So this means that we can remove G from the both side. Okay. So this was added during giving this example. Actually the main functional dependency is A gives C is there. So A matching. So I will add the C variable also as a part of my result. Now, whether any other functional dependency exists now, A gives B, this is covered, this is also covered, this is also covered. Now, CG. CG is not a subset of this. Okay, G is missing. That's why CG cannot be a subset of this, and that's why we cannot add H from here, this H here. CG is not a subset of this. That's why we cannot add I also to the part of this. So here, this result is nothing but a closure. Clear? A closure clear?
Yeah, ma'am, it's clear.
Anybody else is facing a problem with the attribute closure? So here, use of attribute closure is that we will know whether this is a key element or not. Whether this A is a super key of a given relation or not. If consider this complete set, whatever closure elements we have got, if this is equal to the closure say this is equal to the R exactly, then we can say that this left hand side is nothing but a key attribute is there. So if consider we are adding G here, and obviously if G is here, this can be part of this, and Cg is also a subset. So Cg gives I, we can add this. So I also we can add ABC GHI. So this is a complete R. If this is equal to the R, then we can say that this is a super key. The same explanation is written here. So initially we calculate the closure of AG plus. So result equal to AG plus. Now we are having the functional dependency AC and B is AB that can be added because here A is a subset. Similarly, CG is also a subset. So based on CG, H and I also will be added here as a result. And then we can say that AG is a super key. And if consider any of this super subset gives us the complete R, then that can be called as a candidate key also. But if the subset doesn't give us R, then we can say that that is also a candidate key. So this explanation we carried out in the last lecture. Now let us see the uses of attribute closure. So there are several uses of the attribute closure algorithm are there. First one is a testing for the super key. To test if alpha is a super key, we compute alpha plus and check if alpha plus contains all the attributes of R. If it is so, then alpha is a super key. If not, then we cannot say alpha is a super key. Testing for the functional dependencies. So this testing for the functional dependencies, it means that we will know how many attributes are dependent on given alpha. To check if functional dependency alpha gives beta wholes, or in other words that is a F closure, just check whether beta is a subset of alpha plus. So here after calculating the closure, then we will know whether uh, beta holds on alpha. That is, we compute alpha plus by using attribute closure and then check if it contains in beta. And this is very simple and very useful to calculate the F closure also. Then computing the closure of F. So here by calculating all the functional dependencies or all attributes closure, we can calculate the closure of F also. For every gamma, which is a subset of R, we find closure of gamma plus, and for every yes, which is a subset of alpha plus, we put output of functional dependency alpha gives yes. Okay, so that is a way how we can calculate the closure of F by using the attribute set. So here meaning with the last sentence is that here if consider we are having gamma as a subset of R, okay, and we find the closure of gamma plus, and for each yes is a subset of gamma plus, we output a functionality gamma gives yes. This means that whatever here we calculate previously the A plus, okay. So in the A plus we are missing the we are having only these attributes. So if we calculated this is my gamma, okay, this is my gamma plus we have calculated, and gamma is a subset of R. Then whatever the functional yes is a union, sorry, yes will be a subset of this, yes will be a subset of this from gamma plus, then we can say that we will add a functional dependency A gives us B and A gives us C, and we can add this to the closure. Okay, this functional dependencies we can add. So by this way we can go for calculating the closure for what are all gammas we have calculated? For every gamma, we can go on adding these functional dependencies to the closure. And then this will give us the complete closure of F. Instead of giving the attribute closure, from attribute closure, we can calculate the F closure. Clear? Clear? No answers? Okay, let us move to the canonical cover. So F closure, this is also going to add the logical dependencies. So let us come to the canonical cover. So closure was containing all the functional dependencies which are existing as well as logically implied. Consider that F plus is a superset and minimal we are having it as a that is super key and candidate key. Super key it means that this can be a superset also of given elements, but candidate key is always a minimal. Similarly, here canonical cover is there. Canonical cover is a minimal set of functional dependencies which implies all the functional dependencies which gives a minimal set of functional dependency and logically covers all the functional dependencies covered in the F closure. Okay, so let us read the definition of this. I will move to the presentation mode. Canonical cover. Set of functional dependencies may have redundant dependencies that is inferred from others. Just like here we are having A gives C is redundant in A gives B, B gives C and A gives C. Okay, here A gives C is implied, still it is added. So in this way, but here canonical cover, this it means this is a minimal cover, minimal set of functional dependencies. So for example, here a below functional dependency set is given. Parts of the functional dependencies may be redundant. So on the right hand side, okay, so here we are having the right hand side, we are having A gives B. Screen is visible to you. Screen is visible to you. Presentation mode.
Yes, ma'am. Yes,
Uh,
ma'am. It's visible.
uh,
You can continue.
yes. On the right hand side, here we are having A gives B and we are having B gives C. Okay, which implies that we are having A gives C from these two functional dependencies. But one more functional dependency is given, that A gives CD. So here we know that here C is redundant attribute is there. That is already this functional dependency is implied by these two functional dependencies. And hence, in order to get a minimal set of functional dependencies, we only write A gives B, B gives C, and A gives D. Okay, so here whatever C attribute is there, this is adding the redundancy, and that's why we removed that and only given the functional dependency as A gives D. Okay, and this is regarding the right hand side, but there can be redundancy on the left hand side also. Just like if I say A gives B, B gives C, and AC gives D. So AC, it means that here by these two functional dependencies, we know that C attribute is also dependent on the A. Then here we can remove the C here. And that's why we will add only single dependency, that is A gives D. So this here we are having C extra on the left hand side, and we are having C extra on the right hand side. Okay, so canonical cover, it means that this is a this set, the minimal set of functional dependency. So let us read the definition. Intuitively, a canonical cover of F is a minimal set of functional dependencies equivalent to F, having no redundant dependencies or redundant parts of the dependencies. So, okay, here we are removing the redundant parts which are implied, that are removed, and only minimal things are kept in the canonical cover. Clear with the definition? Whether my voice is clearly audible to you?
Yeah, ma'am, it's clearly audible.
Okay, let us go for the canonical cover in detail. So here, whatever the extra attributes are there, it means here if C is implied, still it is added. Here C is implied, still it is added. Such attributes which are not there in the canonical cover, such attributes are called as extraneous attribute. Extraneous attribute, removal of those attributes doesn't change the functional dependency. Okay, that is the meaning of extraneous attribute. So let us go for the next example. Consider a set F of functional dependencies, and the functional dependency alpha gives beta in F is there. Okay, so the attribute A, okay, attribute A is extraneous attribute. It means this is the extra attribute in alpha if alpha belongs to, sorry, A belongs to alpha, and if removal of this attribute, if alpha A is belonging to alpha, and F logically implies F minus alpha gives beta, that functional dependency we removed, and we added the functional dependency alpha minus A and gives beta. So this, if after removal of A and we are adding the functional dependency, if it is implies the same F, then we say that A is a extraneous attribute. Now let us go for the example. Okay, this is regarding the left hand side. Right hand side also same. Uh, okay, let us come to the this example. Who is Aniruddha Jagtap? Okay, let us focus on the first rule first. Aniket Jagtap. Who is this? So, okay, let us concentrate on the first rule. Okay, A gives B, this rule is there. B gives C, this rule is also there. And A gives CD is there. Now here, A gives B, that we cannot change. It means on the both side we are having the minimal set of the elements, that only single element is there. And B gives C, here also we are having the minimal set of the element. That's why we cannot remove any of the attribute. Now let us see regarding this functional dependency. Okay, so here we are having this as a alpha and this as a beta. Actually, example should be in the reverse direction. Okay, so this is my alpha and this is my beta. Okay, so alpha equal to AC is there. Now the attribute A is extraneous. Instead of A, I will use the C attribute. Okay, C is extraneous in alpha if C belongs to alpha and this rule. Okay, now C belongs to alpha. The first rule is applied. So when we can say that this is a extra attribute, when if the following condition holds, that this is a F set, F should be logically implied. So F, within the F, whatever this F is there, from this we will remove this functional dependency. So whatever alpha minus beta, right now this is my alpha and this is my beta, this functional dependency we will remove. So whatever F is there, so F minus the functional dependency A gives C, that will be removed. Okay, and union alpha minus C. Okay, so alpha minus C, from this if we deduct the C only remains with the A. Okay, so if we are having the functional dependency A gives beta, so beta in this example is a B. Okay, so this is my beta, copy, and here we will use this D and check whether this is equivalent to the previous F only. Okay, so if consider we removed this functional dependency and instead of that only this functional dependency is added. So F is nothing but this set. Okay, from this set we remove the current functional dependency. So this should be enclosed in bracket. So if we remove this functional dependency we will remove. Okay, and union to that, union it means that combining the two sets. Now this, now we wanted to check whether AC gives D is dependent. Here A gives B, B gives C. It means A gives C directly. This functional dependency also exists, and hence will not be any change, logical change into the this C and this F. So if this is so, it means that C is an extraneous attribute in the given functional dependency. Clear?
Yes, ma'am, it's clear, but your screen is not visible again once.
Now check.
Okay.
Let it load. Whenever I'm shifting to the chat window, it shows the nested loop. That's why I changed to the window.
Okay, now it's visible. Just it's clear. Means just wait for a while. Means because I have to see once again.
Okay, whether A B C D E F is visible, type the contents.
Hmm.
Okay.
Ma'am, hello.
Yes,
Yeah, ma'am. It is completed.
completed. Okay. So let us go for whatever the example we have seen. That was regarding finding the extraneous attribute on the left hand side. Now let us go for the example which will check for the extraneous attribute on the right hand side. Okay. So same example is there. After removal of that, if it is gives the same set exactly, then we can say that this is the extraneous attribute on the right hand side. So here, instead of A, we are having the C attribute. Let us check whether attribute C is extraneous. We are from this point. Okay. So attribute C is extraneous in beta. So this is my beta and this is my alpha. That C belongs to the beta and the set of functional dependencies F. From the F we removed this and added one more functional dependency after removal of C from the beta. So this means that we are going to have this as functional dependency. So alpha minus beta, that is nothing but our this functional dependency. If we remove this from our F and A alpha is my A, so A I will replace. Beta is nothing but my CD. From the CD, we removed C. So F remaining after deduction of this functional dependency from the F will be only this much. Okay. And union with A gives CD minus C will give us only D. Yes, this will be again same. A gives B, B gives C, and A gives D. So then we can see that this is logically equivalent to the given F only. Then we can say that we have removed extraneous attribute from the right hand side. Please go through this example also for a minute. Done.
Yes, ma'am.
So you can no need to write already. So here implication is that implication in opposite direction is trivial in each case as above. Since stronger functional dependencies always imply a weaker one. So this is a complex statement. We will not go for this. Here we can go for extraneous attribute. Here B in the second dependency is the extraneous attribute. Because here already a functional dependency A gives C is given and AB gives C, it means that there is no any um, that B removal will also give us the same dependency. In the last example, we can remove the C from the second dependency, but D we cannot remove. So here, problem is that on the D is dependent on the AB both, but we already know that C is dependent on the A, and that's why we can remove the C from the second dependency. And in the first case, we can remove B from the left hand side, and here we can remove the C from the right hand side. Okay, because A gives C, this functional dependency is already given, and that's why dropping this functional dependency doesn't make any change. And here, whenever we are dropping the C, here still the functional dependency is preserved at A gives C. A gives C, it means that C is not dependent on the B. It is completely dependent on the A only. And but whatever D is there, there is no other functional dependency which implies that D is dependent on A or B. Okay, that's why we will keep this functional dependency A gives D. So removing C won't affect any change. May I move to the next slide?
Yeah, ma'am. You can move further.
Okay. So testing can be done. Testing if an attribute is extraneous. And so consider a set F of functional dependencies and the functional dependency alpha gives beta is there. In F, to test if attribute A belongs to alpha is extraneous in A. If consider we compute the closure of attributes other than that attribute, right? And using the functional dependencies in F and check whether it contains beta. Okay, do not it means the same set exactly the previous attribute. In if it is does, then A is the extraneous in alpha. So for this purpose, we can go for checking this. And here this is for the right hand side. Uh, let us go for the example of this. So here we wanted to check whether B is extraneous here or not. Okay. So let us calculate the closure of A. So A closure we can calculate by using. So initially we will keep A only. So then A gives C is available. So we can add the C. Okay. And so any other functional dependency is not given for the A. So AC will be the given closure for the A. Now, so to test if attribute A belongs to alpha is extraneous. So here our alpha is AB. Okay. So alpha is equal to AB is there. So we wanted to check whether here B, right now we wanted to check this for the B. So now we wanted to check whether B belonging to alpha is extraneous or not. So for this purpose, we will calculate the closure AB minus our B is a which attribute we wanted to check. It means we wanted to calculate the closure of A plus, okay. From AB, if we remove B, we will remain with only A. So using the dependencies in F, so we will calculate the A plus and check that. So if this is containing the right now, if this contains a beta, right now, if this is our alpha, this is our beta, contains beta. Yes, this set contains beta. That is a C attribute is available. If it is that so, A is a extraneous in alpha. Now here, whatever A closure is there, that contains a beta part, and that's why B is a extraneous in the alpha. Clear?
Ma'am,
Uh, yes.
explain once again that fourth step. I
Okay.
didn't understood it.
Okay. I will take another example. Okay, so we wanted to check whether this C is extraneous. Okay, so whatever A is there, that I will replace with the C. So that you will understand. So now here, to test if attribute C which belongs to alpha, right now we are talking about this functional dependency. So my alpha, it means A is there. No. I think I have taken the wrong example. Example should be this one. No, it is not. So here my alpha right now. So here this functional dependency is minimal. This functional dependency is also minimum. And we wanted to check whether this C is extraneous in alpha. Right now we are talking about this functional dependency. So I will bold this and we will also make this as red. So we wanted to check whether this C is extraneous in alpha. So this is my alpha. and this is my right now beta. Okay. Now we wanted to check whether C is extraneous in the alpha. So what we will do, we will compute the closure of attribute set. Okay, whatever alpha elements are there, from that we will remove the C attribute and will calculate the closure. Okay, so here AC minus C will give us only A. Okay, from AC, this is my alpha. From this, if I remove C, then only A will be remaining. So we will calculate the alpha plus, that is A plus, that is the closure of attribute A, and whatever, wait a minute. Sorry, I was having a call from the office. So here we wanted to calculate the A closure. Now alpha minus C, AC minus C will give us only A, and we are willing to calculate the closure of that attribute. So A being a part of this left hand side, we will apply the reflexivity. A will be already there. So B, so B will be added. Sorry, here as B is dependent on the A, so we will add the B also. And on the B, C is also dependent. So if this is the part of C, it means C is dependent on the B, then we will add the C also. Okay. So now how the calculation of this ABC is done, clear?
Yes, ma'am, it's clear.
Okay. Okay. Now here this first step is done. That calculation compute the attribute closure using the functional dependencies in here. And now we wanted to check whether whatever the attribute closure we have calculated, this contains beta. Right now, my beta is a uh, beta is D. So now, shall we limit our discussion up to this much? As AC, on this D is also dependent, and AC is a subset of this ABC, and that's why we can add attribute D also here. While calculation of the attribute closure, we know that whatever if this is a subset of this closure, then we are adding the gamma. That is, if beta is a subset of this, then we are adding the gamma also as part of this. Okay, and hence we can add D also here. Transitive dependency. AC, both are available here, and AC gives D. It means that I can write D also as part of this closure. And now the last rule says that check whether this closure contains beta. Right now my beta is D. Now D is available into closure. If it does, Yes, it is available. Then C is extraneous in alpha. It means here C is not necessary and C is a extraneous attribute in the given functional dependency. And hence, whatever our C is there, that is an extraneous attribute and that we can replace or we can remove that attribute from the given functional dependency. Let me have the queries. Those who have understood, they can say yes. Those who don't, they can say no. No reply, neither yes, neither no.
Yeah, ma'am, it's understood.
Remaining students.
But ma'am, you haven't written the fourth step like you have written in previous example.
Actually, that step, fourth, this is the first step. That is the calculation of A plus closure. And fourth step is that whatever the closure available is there, sorry. So within that, we wanted to check. Okay, so right now what is my alpha? AC was my alpha and this was my beta, and here AC equal to alpha was there. Okay, and B equal to it was a beta. Okay, and now we wanted to check whether beta, that is a D, if it is available in the, is a subset, is in A closure. Now it is yes, that D is a part of A plus. That's why I have not written the last step. Last step was regarding the same, that is computing this closure and checking whether beta attribute is available in closure. And hence we can say that C is an extraneous attribute in the given functional dependency.
Okay, ma'am, I got it.
Remaining students, any doubt? Okay, let us move to the second example to test if A in beta is extraneous in beta. And for this purpose, we will take this example. Okay, so now we are talking about this example. Okay, right now we are talking about this functional dependency that A gives CD, and here also we wanted to check whether C attribute in beta is extraneous or not. Okay, done. So the canonical cover. Canonical cover is given by F dash, that is F single colon. So we wanted to calculate alpha plus. Right now we are not focusing on this. We're doing this. So here we wanted to check if C is an extraneous attribute here. So we wanted to check the presence of C. So first it says that compute the alpha plus using only the dependencies in F. So we are having the functional dependencies F give F minus alpha minus beta. So whatever this functional dependency there, we wanted to remove. And along with that, we wanted to add this functional dependency. So let us do this. The first step, from the F, we wanted to remove this alpha gives beta. Right now we wanted to check for this functional dependency whether C is extraneous. So we remove, that is minus, it means that we remove this functional dependency from this, and we simply add the functional dependency by removing the C into the right hand side. So this set will be equivalent to this, that minus of this union with alpha, that is A, minus, so in the beta we are having CD minus C will give us D. So we will consider that C got removed. So A gives D. This functional dependency we are talking about, and union, it means that combining the two sets. Okay, these two sets we have combined. The first step is over. Now the next step is that check the alpha closure. Alpha closure, right now our alpha is A. So alpha alpha closure is equal to equal to we wanted to calculate alpha is our equal to A. So we wanted to calculate the A closure. So A closure, initially A will be there as part of this. Next, as A gives B, so we can add this B to the result. B gives C, so we can add C also to the result. And A gives D. Okay, so we can add D also as part of this. So now here, uh, now this result has been done, and now we will check whether in this closure C attribute is there. If it does, it means if check that alpha plus contains a C. Okay, yes, alpha plus contains a C. C is a part of alpha, that is A plus. If it is does, C is an extraneous in beta. So here it means that C is extraneous in this beta, and hence C need to be removed, and this will be the canonical cover for the given C. Done. Okay, let us move to the next point now. Canonical cover. So, canonical cover for the F is the state of functional dependencies FC, such that F logically implies all the dependencies in FC, and FC logically implies all the dependencies in F, and no functional dependency FC contains an extraneous attribute, and each left side of the functional dependency FC is a unique. Okay, here last rule is important, that each left hand side of functional dependencies in FC is unique. So here we are applying union, decomposition, not decomposition, yes, decomposition also we can apply. Such rules we are applying, and then only we are calculating the canonical cover. So to compute the canonical cover for the F, so these rules we are using. So repeat, use a union rule to replace any functional dependencies in F. If we are having alpha 1 gives beta 1 and alpha 1 gives beta 2, then we can apply the rule alpha 1 gives beta 1 beta 2. Okay, so union on the right hand side is done as left hand side is matching. So b1, beta 1 and beta 2 will be combined, that is union. Find a functional dependency alpha holds on beta with extraneous attribute either in alpha or beta. So here we need to check whether there is any extraneous attribute in the alpha or beta. So for this, we test whatever the previous test we have carried out. That test we have to carry out on each alpha and each beta. If no extraneous attribute is found, then delete it from, sorry, if an extraneous attribute is found, we need to delete from this functional dependency. And this we have to repeat until FC doesn't change. Okay. So union rule we are applying, finding the extraneous attribute, and then uh, if extraneous attribute is found, remove from alpha or beta, wherever it is applicable. So we can apply the union whenever there is extraneous attribute is removed, etc. So let us compute the canonical cover for this given functional dependency. A gives BC, BC gives B gives C, A gives B, and AB gives B C. Okay, so let us take this example. So okay, we wanted to calculate the FC. So I will use as f dash equal to. So here we wanted to add those functional dependencies. Here the last rule within that canonical cover said is that we should have only a left hand side to be unique. Okay, so for this purpose, let us check which are the common or matching left hand side. So for this purpose, we are having this and this matching. That left hand side A is there, and here also we are having the matching as A. So that we can apply the union B and BC. We can check this, and hence we can add the rule A gives only BC. So here we need not to, it means union, BC union B. This gives us BC only, and that's why only adding this much rule is sufficient. Okay. Now let us check the second rule. Here, BC gives C. BC gives C. Yes, we can add this. Sorry. BC gives C. This rule also added. And AB gives C. AB gives C. So already we know that B is dependent on the A, and hence there is a this attribute is acting as an extraneous attribute. Okay, as already B is dependent on the A and AB gives C, B is an extraneous attribute in this functional dependency. And already this functional dependency is also given. So it means that B is an extraneous attribute, or A can be also extraneous attribute here. So if we remove B gives C, okay, if we remove uh, AP gives C, within that if we remove A, we will have functional dependency BC gives C. That is already implied. It means A is an extraneous attribute. And if we check for this functional dependency, which attribute is here extraneous attribute? Any idea? In the first functional dependency, which attribute is extraneous? Whatever I have selected, B or C? Okay, one answer B is extraneous.
C, ma'am, C, not B.
Okay, C is extraneous. Yes, already here. If consider, let us check the both cases. If we remove B, okay, so and here it means B we have removed from the extraneous, as we consider that that was an extraneous attribute. Now whether given set this whatever functional dependency set is there, can it imply that B is dependent on the A? Here we are calculating the F canonical cover, and instead of writing these A gives BC and A gives B, we written only A gives BC. So now within that we wanted to check whether C is extraneous or B is extraneous. So here fact is that B is already if we remove B, whatever this functional dependency that B is dependent on the A, that is lost. Okay, and if consider we removed C, if we remove C, A gives B, that is getting preserved, and B gives C, it implies that A gives C, that also preserves. It means that C was the extraneous attribute in the given functional dependency set. Okay, and any other functional dependency is implied and not shown here. Here, this will be the canonical cover for the given set. Done. We done the union, we removed extraneous attribute and added those functional dependencies, and whatever logically implied functional dependencies are there, all the functional dependencies are implied by the given set. So please go through these two, canonical cover and F, and let me know whether any of the functional dependency is not covered in the given set. screen is visible?
Yeah, ma'am, it's visible.
Yes. Whether any sentence is there which is not being covered, which is implied but not covered here.
Ma'am, all functional dependencies are covered. Means I cross checked
Yes.
once again.
That's why this is called as a minimum. Yes. Here, thing is that canonical cover is the minimal set of the functional dependencies, which covers all the functional dependencies which are logically either cover all the functional dependencies, even though logically implied by the canonical cover. Okay, and that's why in many it means wherever gate examinations are there, always you will get this as a sample as a functional dependency set, and then you will be asked to calculate the either canonical cover or either the attribute closure. Okay, or to find out the feature elements can be a super key. Okay, these are the it means common questions which can be asked on the normalization, mostly normalization, that is for calculating the super key, calculating the f closure. Okay, so in the next lecture we will go for such examples. I was waiting to cover this canonical cover. So today we'll stop here. I am facing some network issue and also some noise. So I will share this PPT with you. Whatever drive is there, drive link I have shared with you. So on that drive, I will post this PPT. Okay. So those who are willing to repeat today's any of the points, they can ask me to repeat. So we today studied about the canonical cover and how to compute this canonical cover. Before that, we seen in the example coming extraneous attributes. So extraneous attribute are those attributes which after removal implies the same functional dependency. Okay, these can be on the left hand side or these can be on the right hand side. So we have seen how we use these for calculating the super key and calculating the functional dependencies and testing the final closure of the dependency. Only we seen this much today, and also we covered how examples on canonical cover, computation, and removal of extraneous attribute. And in the next lecture, we will study. So we will have next lecture on the coming Monday, that is middle session. Instead of software engineering, database lecture will be there. So we will stop here today. So you can leave the meeting. Those who are willing, they can can ask me the question if you are facing any doubt.